In mathematics and computer science, the bit predicate or Ackermann coding, sometimes written bit ij, is a predicate which tests whether the jth bit of the number I is 1, when I is written in binary. History. The bit predicate was first introduced as the encoding of hereditarily finite sets as natural numbers by Wilhelm Ackermann in his 1937 paper, The Consistency of General Set Theory. Each natural number encodes a finite set and each finite set is represented by a natural number. This mapping uses the binary numeral system. If the number n encodes a finite set A and the ith binary digit of n is 1, then the set encoded by I is an element of A. The Ackermann coding is a primitive recursive function implementation in programming languages such as C, C++, Java, or Python that provide a right-shift operator greater than and a bitwise Boolean and operator, and the bit predicate bit ij can be implemented by the expression I greater than j and 1. Here the bits of I are numbered from the low-order bits to high-order bits in the binary representation of I, with the 1's bit being numbered as bit 0. Private information retrieval. In the mathematical study of computer security, the private information retrieval problem can be modeled as one in which a client, communicating with a collection of servers that store a binary number I, wishes to determine the result of a bit predicate bit ij, without divulging the value of j to the servers. Chor et al. 1998. Describe a method for replicating I across two servers in such a way that the client can solve the private information retrieval problem using a substantially smaller amount of communication than would be necessary to recover the complete value of I. Mathematical logic. The bit predicate is often examined in the context of first-order logic, where we can examine the system resulting from adding the bit predicate to first-order logic. In descriptive complexity, the complexity class fo plus bit resulting from adding the bit predicate to fo results in a more robust complexity class. The class fo plus bit of first-order logic with the bit predicate is the same as the class fo plus times of first-order logic with addition and multiplication predicates. Construction of the Rado graph. Ackermann in 1937 and Richard Rado in 1964 used this predicate to construct the infinite Rado graph. In their construction, the vertices of this graph correspond to the non-negative integers written in binary, and there is an undirected edge from vertex I to vertex j for I less than j, when bit j, I, is non-zero.